Bien. Right. All right. Maybe, maybe not. All right. So, I'm Andres. I write virtual machines, and I work at Labware. So, why to give this talk? I have some reasons to give this talk, but this so happens to be that this is a ridiculous coincidence of things I never thought would happen, and I am compelled to say something about it. So, and that too. So, yes, it turns out, so Sebastián Sastre, came over there, and I was just with the Canadian user group of Smalltalk saying, hey, you should come to Smalltalks because it's kind of cool, blah, blah. Oh, yeah, sure. Yes. Turns out that I didn't remember at all, but when we were kids, we were swapping games, and he knows my apartment and all that, and we didn't notice until an hour ago. So, yes, exactly. So it's really strange to meet again. Speaking of that, there's another coincidence that I am compelled to talk about, because I've been doing Smalltalk for 18 years, and after 18 years, sometimes time does these things where everything is together at the right time in the right place, and then interesting things happen. Not much. So, some years ago, I was taught Smalltalk by this guy, right? And he goes, hey, he was teaching me math, right? So, hey, by the way, you must prove that the code is correct. It's not enough to merely think that your code works. That's very nice. And by the way, you also have to learn Smalltalk, which he did. And math and Smalltalk go very well together. I'm going to be talking about that Friday. But the path he set me on led me to this. This is a page of improvements to the art of computer programming. That's because of you. The improvement to the art of computer programming, that's yours as well. That was not enough, because after I went to the United States, I met John, right? And he was very nice, but you must write your code artfully. Stop being so much in the face of the code. Remove yourself from the picture. Write in the third person, not the first person, because if not, you force the code into doing the things you want. It's so much easier when you remove yourself and you just do like this, and then things happen, and then you observe. So much easier. You don't even waste your mind, saying, bit number 3, you better. And about that time, I developed an understanding, what I thought was an understanding of these ideas, and I decided to make a test, because you have to prove things correct and not just think they are. I entered into a coding contest, and it had like 63 hours, you have to make some games work, whatever, and instead of just writing any random code, I wrote a framework, and the contest solution was an application of the framework. And then you go to the finals with random changes thrown at you, and you win by writing one method that returns a string, creating one class, doing one push-up, writing one method. Done. And you win, right? That's yours as well. And then Leandro said, at about the same time, hey, you might as well write books while you're at it, because, hey, because why not? Right? Yeah, sure. And I started working on that while I was working at JP Morgan, ridiculous hours on the weekend. So because I had nothing to do on the weekend, because it was, oh my God, JP Morgan. And so, okay, I'll write books, sure. Those are also yours. And after all this happened, about 7 years ago, I met this guy. I said, yeah, that's very nice, but you must learn to look at things from radically different points of view. And it takes a while to get used to this idea that you have to question things, not just, depth first, but breadth first. You have to look at things in a radically different points of view, and only then you understand. Of course, he's talking about this. You know who that guy is? Socrates. And Socrates' method of taking something and effectively bashing it to pieces with questions to see if it resists, when you apply that to your ideas long enough and in an honest enough way, you actually get to something that survives rather stiff tests. Maybe those are suspects of something that works. And teaching me that, and these awesome Skype conversations, this is not a joke, those awesome Skype conversations, I'm very grateful for that. That is also yours. So thank you guys. And it's kind of a ridiculous miracle that the three people that mentored me the most over these 18 years are finally together in the same room. So it's great. So now I get to do this. Speaking of questions, I got this question at the last talk I gave at ESUG. Hey, do you find there's a way to write code small the first time? Because it's so much easier, when you write a bunch of code to go clean it up. It's kind of fun, but it's sort of mechanical, so kind of write it short. That was a question to a presentation, right? So the first answer that I thought of was, well, quoting Dr. Hatch over there, you must learn to throw away your old code. But that's a very short answer. And it was made in the context of many 20-hour Skype calls, etc., right? It's only there that it makes sense. So I'm going to try to make a better answer, a more explicit answer. So first off, why? Right? Not just how, but why also. Because if I just tell you how and you're not compelled, then why bother? So why? Why? Because of this. Because we found together that when you kill code like that, that's lines of code over time. That's some random virtual machine losing 35% of the code. This happens. Delete code, you get more tickets done. Right? So it has a tremendously positive impact on your productivity. There's more to it than that. So I decided, I've observed this many times before, but I decided, well, okay, let's not just take a guess, and rather take a look at what happens in reality. So this is number of times floating point gets mentioned monthly on some mailing list. And you notice the phenomenon, right? So there's this background noise. I don't know, they could be talking about a floating point on the screen or whatever. But every so often, bang, bang. What are these spikes? Well, is it just one mailing list? No. The same thing happens on another mailing list. Over the last 16 years, right? Spike, spike, spike. What is it? And when you go look, it turns out, oh, hey, I have this behavior I can't understand. And quickly, extremely quickly, the discussion becomes about, oh, this doesn't comply with IEEE. What is the meaning of none? Da 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 da. And the fact, you could take one spike, right? So something like spike, and then it decreases and an error comes back because, then something got changed, and then the problem stopped being a problem, and then it was done, and it's the last time you talked about it. But the fact that it repeats is telling you something, right? It's telling you something might not be complete, and that's why it keeps coming up. Now imagine you do that with floating point and many other things, and now you have these periodic spikes of churn. And the time you spend dealing with this is time you don't spend fixing it. Oh, okay. So it's not just your own productivity. It's everybody's productivity. What everybody's talking about. What everybody's spending their energy on. Oh. There are so many reasons for that, I suppose. One that comes from time to time is this 80-20 rule, where an assertion is made that if you just spend 20% of the effort, you get 80% of the results. Well, obviously then, I guess just be happy with 80% forever, because you'll never put in more than 20% of the effort that was required to get something complete. But then you get churn. And then you never get back to finishing it, right? So you're always stuck in there. Now, we could talk about that and the fact that, yes, not all the effort one puts in and the difference between the productivity, etc. Let's dig deeper. Where did this rule come from? Yes. And what was he thinking about when he made this observation? He was thinking about this. Pea plants. Plantas de arvejas. You go, what? What do you mean, arvejas? Seriously? No, seriously. The observation was, 20% of the pods, 20% of the vainas, make 80% of the peas. So, el 80% de las arvejas sale del 20% de las vainas. Hey, so, hang on. So, seriously, we are using a pea plant rule to talk about software. Okay. Wait. Right? Okay, it could be, right? But that also means that there's context transfer there, right? Because then a program is this, right? That's a program then. With all the little pieces the same, except, but this is different size. And this has, this looks like a little tomato, and that looks like a little... Yeah, but they're all peas. And we all know that programs are not this, right? But following on with the analogy, well, that also means that this is an app store, right? Hey, here, I'll get the olive program. Or I'll get the, whatever, random candy program over there, right? Okay, look. It doesn't quite work that way. And here's kind of why. And it's ironic that I have to bring this up, because this is the discretized variety of the 80-20 rule, Zipf's law, which says basically that whatever is frequent, there's a, let's cut to 20%, right? So whatever is frequent tends to be short. And this happens with words and many other things, right? You end up saying you, I, the, a lot, right? But you don't say supercalifragilisticexpialidoso all the time because, hey, supercalifragilistic, right? So, well, okay, but that means that if we only put 20% of the effort, chances are we're going to be always talking about the 80% of the words. And there is more to software than 4-letter words, right? So, in other words, we're talking about the difference between food in a meal. There is more variety to software than this. So this is why. Because if you don't get nutritious meals, you get sick. And then you pay the consequence of the lack of variety and diversity. This is why. But how? There's a couple ways. And I'll illustrate with an example. Not meant to complete, but it's meant to illustrate the different things you end up thinking about. Right? So, well, speaking of floating point, let's take that assertion. 1720 equals 0.85. Should evaluate to true in most small talks, whatever. So, what's that? Okay. So, it should evaluate to true in most small talks, but whatever. Okay. So, why does that happen, right? And now we're going to start asking with the Socratic method here and start asking questions. But first, we're going to ask a certain kind of questions. So for instance, hey, so that's awesome that you can divide and you can floating point, so what do you need in order to do that? Right? How do you actually run the calculation? Whatever this value is, how do you do it? Well, okay, so we're depth first, right? So we dig more. And so, well, okay, could be C libraries, because some primitives are implemented in terms of functions. They call the C library. So now you also have to be aware of C libraries. Of course, for each platform they change. You could be using one versus the other, etc., etc. You could also be exposed to compiler intrinsics. And that's more complicated now, because you don't always get the implementation to the intrinsics, or at least not easily. And it's not necessarily easy to control what happens in that. And if you have a JIT compiler, how do you make sure that when you actually JIT code for these primitives that you're actually implementing behavior is compatible with this stuff? Because if you're not, it could happen that you JIT one thing, the compiler does another one, and sometimes the C libraries do something else. And now what does it mean 17 divided by 20 equals 0.85? Well, that's some. So, lovely 0.85, where did that come from? Right? Because you can't just write a floating point number with the bits, right? So there is some translation going on. This is a literal. Turns out that the problem of making floating point numbers out of strings and recovering the string from the floating point number only got solved in a really satisfactory way 2-3 years ago by this algorithm, ESUG, which runs in integers, except like for 5% of the time, it actually needs something more complicated, and that falls back to Dragon 4, which is from 2004. So this is rather new, right? And it's only these, or whatever it is, that gives meaning to this 0.85 in that. So let me see. So now we're talking print string for floating point numbers. Whoops. Yep. Now we're talking print string, right? We're also talking smalltalk compiler, because somebody is making these floating point numbers out of the code. And we're also talking, hey, does that mean that if different smalltalks implement different types of algorithms, that I run this type of expressions in one smalltalk and I get one result on one and one on the other? And what happens if these algorithms are different, yet the expression continues to answer true? Ooh, I don't like that, right? Okay, but then there's the issue of precision, because of course all these operations have certain precision. Everybody knows that. All right, well, so, you know, there's rounding modes for this stuff. You can round up, down, round to even, all sorts of things. So in what mode is the floating point arithmetic being done when this happens? Well, if you're not aware of that, then who knows? Then there's also other stuff like the 80-bit x87 format, because the x87, this is for Intel, you know, but so on the x87, all the operations are done or could be done in 80-bit registers. So that's like a 64-bit register plus another 16 bits that are used to extend the mantissa and the exponent. So that means that if perhaps this division was done with 80-bit arithmetic without you knowing, now you may get to round to something else because you're looking at more, and now what does it mean equal? Or what does it mean this? Right? Oh, how about other FPUs? You like ARM? You like Spark, Power, MIPS, stuff? Same stuff. And now, you may think, oh well, but the 80-bit format, who cares? Well, it does matter, because you can very easily fabricate a piece of C code that says, you know, suppose you have a function called foo, right? And it simply returns a floating point value. And inside of foo, you just write, well, return 1.1 plus 2.2, right? Something simple like that. And now you go outside of that and you write, if foo equal foo, print okay, else printf false, you know, bad. And the C compiler produces code that takes the false branch. How can it be, right? Because if foo equals foo, what do you mean? It's answering a constant. Well, it can happen because the ABI for x87 says you return the answer in the top of the stack of the floating point FPU, which is 80-bit. Now, but I need to call another function. Okay, let's save that to memory, but that's now 64-bit, not 80. Then you call it again, you return 80 bits, you compare the two. Oh, compare the register to memory, they don't match, boom. Right? Oh. What do you mean, right? So, and then let's take a look then at the manual, right? And when you look at the manual, you find, oh, by the way, this is impossible. Damn, Okay, so that's one way of asking questions, right? That's one way. But it's not enough, because now you are constrained like this. You're looking at the tunnel vision. Yeah, sure, you went very far, but you're looking like this. And what about the sides? So let's try again. How about breadth first? So for instance, very nice that it works with that. What about other numbers? Right? Let's be consistent here, because it's great that this might happen or not, but what about other numbers? Well, what other numbers do you know? Well, you have IEEE 854, not 754, and now you're talking decimal floating point. This is not, by the way, this is not a random curiosity. This is actually implemented in hardware these days on power CPUs. And Intel also provides a library that you can link. It's a free library. Well, I think some sort of open source. I forget the license right now. But you can actually take this library, implement it, it's provided to you by Intel, and now you can have decimal floating points. So isn't that nice, right? Because now if you really had decimal floating point, this could actually make sense, right? Because there could be a chance for this to actually be true. But in this case, okay, right? And so if you hadn't looked outside of 754, you would have missed that. Oh, well, what else? How about scale decimal? Should that be equal to? What happens in a general case? Right? Okay. How about single precision or double precision? What about I take the fraction, first I convert it to some single or double precision, and then do the comparison. Does that still work? What about other numbers, right? Because, well, we said other number types, but we could also change the numbers and see what happens. Because, it would be very nice if just one worked the way we wanted, but there's more numbers than 3. So, how about we try this, but first we put in an integer that has bits that don't fit in the floating point mantissa anymore. Now you're losing precision, so what do you mean equal? Or, how about this one? This one is awesome. So, 10 to the 400 is either an error as a floating point, right, or it's infinite. Are you really planning to do comparisons with infinite like this? Right? And when you start looking at these things, you find that, hey, very trivial properties of numbers that you assume all the time are immediately broken and horrible. And in a horrible way. Like, for instance, excluded middle and equivalence. So equivalence, is so nice, because the relationship of equivalence is, the relationship of equivalence itself is a so-called relationship of equivalence in which, for any members in the set, X is related to X, and if X is related to Y, Y is related to X, and if X is related to Y, and Y is related to Z, then X is related to Z. So you have reflective, symmetric, and transitive, right? Oh, really? Well, let's play that game with this guy. 10 to the 400 is equal to infinite, but 10 to the 500 is also equal to infinite, and so consequently, 10 to the 400 is equal to 10 to the 500. What? What happened, right? What do you mean? And speaking of, right, and with all the other numbers too, it's like, and what about this other guy? Nan. So nan, if you look at the manual, it says nan is the only number that is different to itself. So here you have awesome values that are perfectly valid for which x is not equal to x. But you cannot compare them either, right? So if you try nan nan less than whatever, or nan greater than whatever, no, and it's not equal either, so good luck, right? How do you work with that? So, also that means, let's break hashing, because why not? So, right? Because, oh great, 10 to the 400 is equal to infinite, and 10 to the 500 is equal to infinite, so the hash of 10 to the 400 has to be the same as the hash of 10 to the 500. And you're telling me now, and I had to deal with this in person, myself, right? So now you're telling me that the hash of this, and this, and this, and that, and this, and this, and all that, and all this, they all have to sync and match up. You have any notion of the amount of code that this generates? Now your code starts growing like crazy, right? Oh, if it's an integer, you try to convert to a float, but if you can't, then, well, okay, do whatever you were doing before. But if you can't convert it to a float, okay, now you need to convert to hash a float, right? But you want the value to be good. Oh, right. Now you have to take into consideration, oh, I forgot, big endian and little endian, right? Oh, right, yes, sorry. So, I have to convert, then do the bytes in the right order because different platforms change order. I can't take the bytes any which way, so I have to take care of that. Okay, fine, so it's hash. But what if it's a special value because NaN, there is not just one value of NaN. There's a multitude of values of NaN, right? Because it has flags in it that are implementation defined, right? So there's not just one floating point bit representation for NaN. There's millions of them. Also, those have to have this hash. It's the same. Oh, sorry. If it's a special value, then blah, 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 right? And now let's do the same for double precision. Right, but double precision, if it's equal to single precision, now you have, double precision as single precision, then hash, unless you can't do the conversion because it's too large. Okay, fine, then I have to do something else. But it also has to match what you're wasting your time, right? And it is at this point that you ask, like, they have a fabulous story of how many centuries ago, actually, in Russia, there was the observation that this guy that I really like, Yakov Isidorovich Perelman, you'll have to correct the way I say it later, and he pointed out in his fabulous math books, by the way, he was a forester interested in science, and he wrote the best science books for popular science. They're fabulous. So, he wrote, it's really funny that people get so worked up about the number of digits that people do logarithmic calculations with tables of logarithms, and how they insisted that tables must have 14 digits when the measurements they were taking had at most 5 digits of precision. What are you doing? So when you say equal to 0.85, where did that 0.85 come from? Do you mean exactly equal to 0.85 in floating point, or do you mean, well, kind of close to that, plus minus some error bar that I control? Did you really mean 0.85 or 0.84, 99999, 1, 2, 3, 4, 5, 6, 7, right? And if you don't know what it means, why do you have expectations of the answer? Right? So, look at this difference, look at the contrast now between digging depth first versus breadth first. Right? Depth first, you would have been so confined to floating point that you would have been satisfied with some effectively random answer because you were looking at IEEE 754. And if you had written more code to deal with that, chances are you would have broken everything else here. And fixing that, once that code got in, would have required even more code, right? And that's the issue. So an answer to the question of color is this. When you want small code, look at the problem depth first and breadth first. You'll notice several things, you'll learn about a whole bunch of stuff. And now, think you have a matrix of solutions, right? So which ones do you pay attention to? And usually, if that's breadth first and this is depth first, some of the interesting solutions are going to be there somewhere, down there. And the deeper you dig, the better solutions you can find. And the trick here is to pick some solution that satisfies all your requirements, doesn't break stuff, and also reduces the tension in the code. That's almost like the least possible, and perhaps just a tad less. This ambiguity in the relationship outside the boundaries of things that Rebecca was talking about. Be somewhat removed. Don't care so much that it's exact. Because if you care too much that it's exact, now you're inflexible, You have sharp edges, and then you have to account for them with code, which you have to write, maintain, and talk about it because it's always broken. So, I'm sure you can think of many solutions by now. I can give you one. I'm not going to claim it's correct. And of course, one answer that you find is not enough. But for your consideration, how about this? Problem solved. There, bye. Right? I don't care anymore. So, your turn to ask questions.
Very tricky, but in your model, it should have very complete semantics.
Yes, and actually, this slide here, that's why I had to be very careful. I write an answer as opposed to the answer.
Yeah.
I agree. But this only comes in the context of your exploration, of your requirements, which may be different than others, and so on. Now, of course, it's perhaps a tad more difficult if what you're writing has to be used by many others that may not share your requirements. At that point, it's critically important that you start paying attention to that stuff, these things, because then if you don't, you're going to break everybody else, and then you get mailing lists that have the endless spikes or churn, and then you have to answer them. And
the problem is trying to find a solution for all the uses, even for those you don't know yet.
Yeah.
And a way to do that, particularly in this case where there are standards, is to say, well, I'm going to do to the standard, and I'm not going to need more. You're not going to be smart, because I don't know what other people are going to be doing. And because of that, chances are what you write is going to be reliable. Other people can change it, well, that's fine. But it's important that what you do is reliable. Any other questions? Yes.
Okay. Brain, you will.
It's your fault.
Yeah. No, but you did us great for a lot of things you did. But there was one thing I remember that you also followed that other recommendation, but I think it was very important that you did and I want credit for that. I asked you to put exercises in the book. Yes.
Well, yeah, but...
And your first reaction was not to do that, so I had to insist.
No, but look, I mean, your stuff is so big already. I mean... Well, okay, I can put in an exercise. Okay, sure.
Very, very important.
Okay, and I also follow Knut's recommendation of when you find an exercise that was given to you, give the source. I did that too. So, if you have no other questions, then please take them. Okay, thank you.